Okay. Okay. First, let us finish these reactions and then I will come to that. Okay, let's discuss the answers. SO2 plus O2 gives you SO3. Oxidation happens. That means sulfur dioxide is SO2 gets oxidized to form SO3. Now, after balance the reaction, I'll put 2 here, so there are 2 sulfur atoms. I'll put 2 here also, now here also there are 2 sulfur atoms. Oxygen 2 into 2, 4. Here 4 oxygen atoms and here 2. 4 plus 2, 6 oxygen. And here 2 into 3, 6. So here also 6 oxygen atoms. So all atoms are balanced. Second one, CaO. CaO is calcium oxide. Calcium oxide plus water gives me calcium hydroxide. So this is also balanced. Here 1 oxygen and 1 oxygen. So 2 oxygen atoms on left hand side. And here also you have 2 oxygen atoms because 2 is mentioned outside the bracket. So O has 2 oxygen atoms. CO2 plus H2O. Carbon dioxide plus water gives you a particular acid called carbonic acid. That is H2SO3. Carbonic acid. SO2 plus H2O gives you H2SO3. This is called sulfurous acid. And SO3 plus H2O gives you H2SO4. This is sulfuric acid. N2O5 plus H2O gives HNO3. This is called nitric acid. I have to balance it, so now it's balanced. This is called calcium hydroxide. And this is called sulfur trioxide. That are very important reactions for board exams. You have to know the names as well, so I wrote the names. Okay, 3 more reactions and then I'll discuss washing soda. Try these 4 reactions. Okay, 7th one, calcium hydroxide plus carbon dioxide. This gives you CaCO3 plus H2O. This thing causes milkiness. So if they ask you what is the cause of milkiness when calcium hydroxide reacts with carbon dioxide, the reason is formation of calcium carbonate. Next one, calcium carbonate plus water plus carbon dioxide. This gives you calcium bicarbonate. So I can say the milkiness disappears. That means if I ask you a question like this in the exam, what happens when carbon dioxide gas is passed through a lime water? What is lime water? Calcium hydroxide is lime water. It is also called lime water or slaked lime. Lime water or slaked lime is a common name of calcium hydroxide. So what happens when carbon dioxide gas is passed through lime water? Then we can write down this reaction. In the board exam, even if they don't ask you to write the reaction, still you are supposed to write the reaction. Please remember this. In chemistry, if there's a reaction for any particular process, you must write that reaction even if they don't ask you for the reaction in the exam. Then only you will get full marks for that particular question. So you have to explain the process and then write down the reaction. Coming to the 7th reaction, that is calcium hydroxide plus carbon dioxide, we get calcium carbonate, that is CaCO3 plus H2O. The milkiness appears, the solution turns milky due to the formation of CaCO3. Now, if I continue to pass more and more of CO2 through this solution, then the 8th reaction happens. That means if carbon dioxide gas is passed in excess, that means a lot of carbon dioxide gas is passed through lime water, then the milkiness disappears and we get calcium bicarbonate, that is CaHCO3 twice. It's a very common question in the exam. So if calcium hydroxide is reacted with carbon dioxide, you get calcium carbonate, but you pass more and more of carbon dioxide gas, then you get calcium bicarbonate, that is CaHCO3 twice, due to which the milkiness disappears and the solution again becomes clear, clear or transparent. The solution again becomes clear, CLER, clear, clear or transparent. Why clear or transparent? Because milkiness disappears. Why does milkiness disappear? Due to the formation of CaHCO3 twice. Ninth one, this sodium bicarbonate, also called baking soda, NaHCO3. If I heat it, I get Na2CO3 plus H2O plus CO2. These are the three products obtained if I heat NaHCO3. In order to balance it, I will put a 2 here, and now this equation is balanced. Last reaction, Na2O plus HCl. Now, HCl is an acid. HCl is called hydrochloric acid. Sodium oxide is a basic oxide. How do I know it's a basic oxide? Because sodium is a metal. Most of the oxides of metals are basic in nature. So if a basic oxide reacts with an acid, we get salt and water. So this is neutralization reaction. The salt will be NaCl and water is H2O. I need to balance the reactions. I'll put 2 here and I'll put 2 here. Now it's a balanced chemical equation. Milkiness means that the solution becomes turbid. The solution becomes turbid. Turbid means it's no longer transparent. So it turns milky. That means you can't see through it properly. If you look through the glass of test tube, then the solution will not be a clear, transparent one. It will be cloudy. That cloudiness will appear, the turbidity will appear. That's called milkiness. No, milkiness does not mean transparent. Milkiness means it is not transparent. It is the opposite. Milkiness means you cannot see through the solution. When there is no milkiness, that means that it is transparent. So when the milkiness disappears, then you can call it transparent or clear. But when there is milkiness, it is turbid, Turbid, turbid or cloudiness. Okay, washing soda. So first of all, washing soda is what? Washing soda is a particular chemical substance which is represented by this formula. This is called washing soda. You have to write dot 10H2O mandatorily. It's mandatory. If you don't write dot 10H2O and just write Na2CO3, you will definitely lose marks. The complete thing is called washing soda. And the chemical name of washing soda is sodium carbonate decahydrate. Sodium carbonate because Na2CO3 is called sodium carbonate. Decahydrate means there are 10 molecules of water of crystallization. Deca means 10. Hydrate means water. So decahydrate means 10 molecules of water are attached to one molecule of Na2CO3. So the name of washing soda is sodium carbonate decahydrate. Now, the raw materials to prepare the raw materials to prepare washing soda. In the exam, they ask you, how do you prepare washing soda? So the raw materials used to prepare washing soda are NaCl, water, carbon dioxide, and ammonia. These are the four major components that are going to be used to prepare washing soda. So, firstly, what happens is this solution of NaCl in water, that is NaCl plus H2O, this entire thing is reacted with ammonia followed by carbon dioxide. All these four react together. These react to give you two different components. One is this, and one is this. So NaHCO3 is one product formed. The other product formed is NH4Cl. This is the starting point to prepare washing soda. Then this NaHCO3, you see I have put a downward arrow indicating that it is a precipitate. A downward arrow indicates the formation of a precipitate. Since it is a precipitate, it can be easily separated from the remaining solution by the process of filtration. So you obtain that precipitate, you take it out, and since you isolate it from the solution, you can now take it further for this reaction, that is, you heat it. If you heat it, you get Na2CO3 plus H2O plus CO2. So step 1, step 2. And now this Na2CO3 is reacted, or is rather dissolved in water and crystallized to get this. These are the 3 steps. This entire process is called Solvay's process. So if they ask you which is the method used to prepare washing soda, you will see that it is Solvay's process. What happens in Solvay's process? These are the 3 steps which happen in Solvay's process. Now, this component which you had, that's also utilized. Now, how is that utilized? This is taken and it is reacted with calcium hydroxide. If I do that, I get these as my products. This ammonia is obtained again. So can I say that in the first step, I started with ammonia as a raw material, and when I react NH4Cl with calcium hydroxide, I again get ammonia back. So this ammonia can be further circulated and recycled. Now is washing soda clear? Okay. Just remember that I say, if I just write Na2CO3, this is not washing soda. Please keep this in mind. This is not washing soda. Why? Because I have written only Na2CO3. If I write Na2CO3.10H2O, then it will be washing soda. So if I just write Na2CO3, this is called soda ash. So Na2CO3 is called soda ash. But Na2CO3.10H2O is called washing soda. Plaster of Paris is nothing big. It is a very short topic. First of all, plaster of Paris, POP, is plaster of Paris. POP is plaster of Paris. Chemical name of plaster of Paris is calcium sulfate hemihydrate. This is the chemical name of plaster of Paris, and the formula is CaSO4 dot half H2O. This is the formula of plaster of Paris. How do you prepare it? You take gypsum. This is called gypsum. You heat gypsum. You heat gypsum to a temperature of 423 Kelvin. You heat gypsum to a temperature of 423 Kelvin. That means approximately it is how much? 150 degrees Celsius. If you do that, you get plaster of Paris as the product. So plaster of Paris is obtained and the remaining thing goes out as water vapors. So this is POP. POP is obtained in this way, that is by heating gypsum. Now POP has a tendency to absorb moisture from the surroundings. So on absorbing moisture, POP becomes hard as it gets converted to gypsum. So what happens is if you let POP react with moisture or water from the surroundings, it will absorb the water molecules to form gypsum back again. Again, it will get gypsum. That is why we ensure that we store POP in waterproof containers and also airtight containers, because else it may absorb moisture from the air. Any doubt in plaster of Paris?
No, sir.
No, sir.
Okay. Any doubt from any other chapter? Any reaction or any other concept? Okay. Okay, I'm asking a question. Try to answer it. Okay. There's a question. In this process, in this process, what kind of reaction is shown in this process? What kind of reaction is shown? Try to solve this. I'm giving you 2 minutes. So what is the answer? Okay. So see, what is this E minus? E minus, what does this mean? E minus means electron. That's the first thing. E minus means electron. Now please try. E minus means electron. Now plus is given. Plus, that means on the reactant side of the reaction, that is on the left hand side of the arrow, you have a process wherein electrons are being accepted. You have a process wherein electrons are being accepted. How do I know that? Because I see plus electrons. On which side do I see plus electrons? I see plus electrons on the left hand side of my reaction. If I see plus electrons on the left hand side of the reaction, that means electron is being accepted by the reactant. So plus electron on left hand side of a reaction means electron is being accepted or gained by the reactant What is gaining of electrons called? Gaining of electrons is called. Yes, what is gaining of electrons called? Gaining of electrons is called reduction. Gaining of electrons is called reduction. So, in the reaction, given in question, the reactant, that is this one, has got reduced. That means the reaction is a reduction half reaction or a reduction process. So this is your final answer. Look at the question once more. Plus 6 electrons on the left hand side. Left hand side showing plus something electrons means that the reactant is undergoing reduction. Because it is gaining electrons. Note, this reaction is only a half reaction. As it involves only reduction. So it is not redox. So this is a very important point. This is not a redox reaction. This is only a half reaction. What type of half reaction is this? It is a reduction half reaction. Whenever you see electrons involved in the reaction, that means it is always be a half reaction. It can never be a redox reaction, because a redox reaction will not have any electron present in the reaction. Whenever you see electrons mentioned, it is definitely a half reaction, like in this question we had. So it is a half reaction. It is not a redox reaction. What type of half reaction is it? It is a reduction half reaction. That means, can I say now I can see that electrons are written on the right hand side, plus electrons on the right hand side of the reaction. Now I see that the electrons are written on the right hand side of the reaction, plus 2 electrons. So plus 2 electrons is written on the right hand side of the arrow. Therefore, this is an oxidation half reaction. This is an oxidation half reaction. Why oxidation? Because there are electrons shown on the right hand side. But this is not a redox reaction, because in a redox reaction, you will never come across electrons. So this is an oxidation half reaction. That's all. It is not a redox reaction. Any doubt?
No, sir.
Okay. So let's start with the chapter, remaining portion of metals and non-metals, because doubts are over. Last time we completed the formation of an ionic bond between a metal and a non-metal. We saw the reactions of non-metals, we saw the reactions of metals, we saw the reactivity series of metals. Now we start with the process of obtaining the metals from the natural sources or deposits found. So how do we obtain the metals? There are so many metals obtained in the Earth's, which are present in the Earth's crust. So metals are present as natural repositories. There is a natural mineral or there is a source from which we will obtain a particular metal. Okay. So let's understand the terms one by one. The naturally occurring substances in which metals occur in the Earth's crust are called minerals. So those natural repositories, those natural rocks or the substances which are found in the Earth's crust containing the metals are called minerals. Now, the minerals which can be used by human beings to obtain the metals profitably are called ores. That means what? If I have a source of a metal, that is just called a mineral. It need not be necessarily an ore. Why? Because it may not be very easy for me to take out the metal from that mineral. It may be very costly because the quantity of metal in that mineral could be very scanty. It may be a very low amount. It may be a small amount of metal. So it may not be very profitable for me if I want to carry out the extraction. That means that will not be called an ore. An ore will only be that particular mineral from which I can obtain sufficient quantity of the metal and I can sell it and I can earn money from it. So profitably word is extremely important when you define an ore. So the ore is such a mineral from which the metal present in that can be conveniently and profitably extracted and then sold or used for commercial purposes. So I can say all ores are minerals, but all minerals are not ores. All ores are minerals, but all minerals may not be ores because from all minerals, I may not be able to obtain the metals profitably. So I cannot call all minerals ores. But the ores are definitely minerals. Aluminium is the most abundant metal in the Earth's crust. You have to know this when I ask you. Okay. Now, a metal which has very low reactivity. Last time we discussed the reactivity series. So if you look at the bottom of that series, towards the bottom or towards the end of that series, you will find metals like gold, silver, platinum, and copper. So a metal which has a low chemical reactivity occurs in nature in the form of native metal or a free state of metal. What is the meaning of native state or free state of a metal? That means the metal is found as the metal itself. There is no compound of it. It is not existing as its compound like oxide or sulfide. No, it is present alone. So the metal itself is present. It is not in combined state. It has not formed compounds with oxygen or sulfur or any other species, and therefore it is alone present in the rocks. If a metal is present alone without any particular oxygen, I mean without any other element combined in it, definitely we'll call it free state of the metal. So no other element has combined with the metal to form any compound, and therefore the metal is existing completely free or in the native form. So if the metal is in its native form, that means it is not yet in the combined state. It has not undergone formation of oxides or sulfides or carbonates. That means it has not been easily attacked by oxygen or sulfur or carbon dioxide present in the atmosphere. Why so? Because it is less reactive. It does not react easily with the moisture present or with oxygen present in the atmosphere. And therefore, it is existing alone in the free state. Examples of such metals are gold, silver, platinum, copper, etc. On the contrary, a metal is said to occur in its combined state if it is found in the form of its compound. Examples of metals found in combined state are magnesium, calcium, potassium, etc. Say potassium, calcium, magnesium are reactive metals, and therefore they tend to react easily. Since they are reactive, they will not exist alone. They will exist in the combined states. Combined in the sense they will form compounds. So calcium may form compound like calcium carbonate. Magnesium may also form a compound like magnesium carbonate. So now I cannot call it a native state. I'll call it is in the combined state because it is magnesium carbonate and not only magnesium. It is a compound of magnesium. Magnesium carbonate is a compound of magnesium. Likewise, calcium carbonate is a compound of calcium. Likewise, potassium chloride is a compound of potassium, and so on. Copper and silver are two metals which occur in the free state, and also they have been found in the combined states. So both possibilities exist for these two metals. Copper forms compounds also, but copper is also known to exist alone, that is in its native form. Silver forms compounds also, and silver also exists alone as silver in its native form. So both possibilities are there for copper as well as silver. What is this process? So the process of isolating or obtaining a pure metal from its ore is known as metallurgy. That means there are many different steps involved in order to carry out the process of extraction of a metal right from its ore. So in its ore, it's present. If I want to take the metal out from the ore, and then if I want to purify it, I have to carry out many processes one by one. This entire set of processes or methods that are used to obtain a metal from its ore are called sequences of steps. Right? So these steps form a part of metallurgy. The entire branch of metallurgy deals with all these processes and steps and methods, techniques which are used to obtain the metal from its particular ore. The major steps involved in metallurgy are, so there are 4 major steps in metallurgy. We'll study each of those steps one by one in detail. So what is metallurgy? Metallurgy means obtaining the metal. That means finally I will have only the metal in my hand. But in order to get the metal in my hand, I have to carry out many processes. I'll have to follow many steps. I'll have to do a number of things so that finally I have the metal with me. From where? From the particular ore of the metal. What is the ore? The ore is a natural deposit which contains the metal. So I can carry out the processes of isolation and extraction. And at the end of these processes, I'll have the metal with me in hand. So if the metal is present at the end of all these processes, that means I have obtained it through metallurgy, because metallurgy involves steps, methods, and techniques involved to recover or to obtain a metal from its ore. So the major steps in metallurgy are, first one, crushing and grinding of the ore. Crushing and grinding of the ore. Most of the ores occur as big rocks in nature. Most of the ores occur as big rocks in nature. Since there are big rocks present, they need to be broken into smaller pieces. There are many rocks. Those rocks will be broken into small pieces with the help of crushers. There are devices which do this. So the devices crush or break the rocks into pieces. Once these pieces are obtained, then the pieces are further reduced to a fine powder with the help of some other type of device called ball mill or a stamp mill. So there are different devices and instruments which are used to crush, grind, and convert to the powdered form. So first we will crush, we will break, we will grind, and finally we will convert the small pieces obtained to a fine powdered form, and the powdered form will be like a powder, and that is why it is called a powdered form. The conversion of crushed ore to powdered form is called pulverization. So first you break the rocks, then you grind and ultimately convert them to a fine powder. So the conversion of the crushed ore to the powdered form finally is called pulverization. That means in the first step we just broke and we converted the rocks to powder. So in the first step we just obtained the powdered form of the rocks. Nothing else has been done in this. Now remember, if you have rocks and if you have the ore present inside the rocks, the ore will be present along with many other impurities as well. Because it is in nature, it is existing in nature. There will be sand, there will be clay, there will be other unwanted dust particles. All those will be impurities present. So the second process after pulverization is concentration of the ore or enrichment of the ore. Concentration is nothing but removal of impurities from the ore powder. Whatever impurities are present need to be removed. What type of impurities? There are impurities like sand, clay, dust. Those impurities will now be removed, and that process of removal of impurities is called concentration of ore, also called benefaction of ore. Benefaction. Either you call it benefaction or you call it concentration. The impurities present are called gangue, Gangue. So just now I said there are sand particles, there are dust particles, there is a lot of clay. All these are called together gangue. So what is gangue? Gangue refers to the impurities. The unwanted materials or impurities like sand, clay, dust, etc. present in the ore are known as gangue. The process of removal of gangue from the ore is called concentration of the ore or benefaction of the ore. Now, if you have to remove the impurities, we have to do some things. We have to follow a particular process. The process that is, or the method which is supposed to be followed for concentration of an ore depends on the type of the ore and also on the type of the impurities present in the ore. There are different techniques. You cannot use the same technique for all types of ores. So there are different techniques. We will study some of them. The first technique that we are studying is hydraulic washing. Hydraulic washing is also called gravity separation. Hydraulic washing is also called gravity separation. What is the meaning of this process? So in this process, the method is based on the difference in the densities of ore particles and gangue. That means what? The impurities may have a different density. They may be lighter or heavier, let's say. And the particles of ore will also have a different density. Usually, what happens is the particles which are impurities, I mean the gangue particles are light and the ore particles are heavier. So water is used in this process. The word hydraulic indicates the use of water. Water is used to wash the impurities away. Water is used to wash the impurities away. That means to wash the gangue away. The gangue particles are lighter than the ore particles, and so the gangue particles will be easily washed away by the water which has been sprayed. So the water which has been sprayed will take along with itself all the impurities, and hence in this way the ore particles will be isolated from the impurities. The impurities will be washed out. Why? Because of the water which has been sprayed or introduced. So the water which has been introduced will wash the gangue. So the gangue is out of the ore particles. It is out from them. So the gangue particles are lighter and the ore particles are heavier. Due to the difference in these densities, we can use this method of hydraulic washing. The method is used for oxide ores of iron and tin. Usually it is used for oxide ores of iron and tin. Let me ask you an exam. Which ores are concentrated by hydraulic washing? Then you can say that oxide ores of iron and tin are concentrated by hydraulic washing. Next type of technique, or the next technique used for sulfide ores, is froth flotation. So the process of froth flotation is applicable to sulfide ores. That means ores of metals which contain sulfur. Sulfide ores. What happens in this process? First of all, oil and water both are used in this process. Oil as well as water both are used in this process. The ore particles, I repeat, the ore particles get wet by oil. And the gangue particles become wet because of water. That means the tendency of the ore particles is to get attached to the oil, and the tendency of the gangue particles is to stay with water. So it is called a preferential wetting. Why preferential? Preferential because selectively you are wetting the things. Some particles are being wetted by oil and some particles are being wetted by water. Who is being wetted by oil? The ore. The ore particles are being wetted by oil. And the gangue particles are being wetted by water. So the impurities are being wetted by water. So water and oil are added to a tank. The tank is called a flotation tank. So it is a tank containing water and pine oil. It's a mixture. Then the ore particles, that is the entire ore along with impurities, is that present in the tank. Then a blast of air is blown. That means you are passing air. You are passing air through the pipe from the top to introduce froth. Froth means what? Froth means bubbles. Froth means here the bubbles which are produced. So froth is produced by introducing highly compressed air. So air is passed. That air is passed through the pipe of a rotating agitator. The agitator will produce the froth uniformly because it will keep stirring and moving. Once it rotates and moves continuously, it is easier to generate froth. So air has been passed, right? Air has been passed, and also the agitator is rotating. Because of the rotation of the agitator, it is easier, or rather, you can say faster, the froth is produced. Froth means the bubbles. Now, the gangue particles are wetted by water, so they will sink to the bottom of the tank, whereas the ore particles who are wetted by oil rise up along with the froth. So now we have separated the gangue from the ore particles. How have we separated the gangue from the ore particles? The gangue has settled to the bottom of the tank. The gangue, because it was wetted by water, has gone to the bottom of the tank. Whereas the ore particles who were wetted by oil rise up along with the froth. They get attached to the froth and hence they become lighter and they start rising upward. So the froth containing the ore particles is on the top surface of the tank and so it can be skimmed off easily. Skimmed off means you are removing it from the surface. The froth contains the ore particles and you have removed the entire froth containing the ore particles from the top surface of the tank. So the gangue particles settled at the bottom because they were heavier. They settled at the bottom, whereas the ore particles became attached to the froth and so they rose up. Since they rose up, they were separated or they were skimmed off along with the froth. So now we have separated the ore particles from the gangue. The gangue particles remained at the bottom of the tank and now they can be thrown away. This method is used for concentration of sulfide ores. So froth flotation is used for concentrating sulfide ores. Next way of concentrating or removal of gangue is magnetic separation. Next way of removal of gangue is magnetic separation. Magnetic separation, as the name suggests, will have something to do with the magnet or the magnetic properties of something. So the method depends upon the difference in the magnetic properties of ore and gangue. If the gangue particles do not get attracted to the magnet, but the ore particles get attracted to the magnet, then definitely I can separate them using this principle. The magnetic ore particles will get attracted towards the magnet and hence they will fall at a distance. Because they have been drawn close to the magnet, they will be away. And they will fall somewhere else when you introduce the particles and the gangue together on the top or on the surface of a magnetic substance which is moving. What will happen? It's like a conveyor belt. The conveyor belt moves slowly and slowly. Similar to that, here the magnetic roll will keep moving. And once you pour the ore particles and gangue particles together on that belt type structure, that is a coil, I mean, the part which is moving, which is magnetic, of course, then what will happen? The gangue particles will be away, they will fall down. And the ore particles will be attracted towards the magnet and so they will fall somewhere else. So they will fall at a distance. They will fall at a distance from the non-magnetic gangue. So the ore particles will get attracted towards the magnet, whereas the gangue particles will not get attracted towards the magnet. Due to this, they all will get separated from each other. The ore particles will be obtained at a distance from the gangue because gangue did not get attracted towards the magnet, whereas the ore particles got attracted towards the magnet. This method will be used for concentration of iron ores. Why iron ores? Because iron is magnetic in nature. Iron is magnetic in nature. Iron gets attracted towards the magnet. So for iron ores, we can use this type of concentration. So we discussed three different techniques of concentration. First was hydraulic washing. Second was froth rotation. And third was magnetic separation. The next step is the third step. So in metallurgy, as I said, there are four major steps. The first step was what? The first step was crushing and grinding of the rocks. Crushing and grinding was the first step under metallurgy. The second step under metallurgy was concentration of the ore, under which we studied the three techniques. The third step of metallurgy is extraction of the metal from the concentrated ore. Once the ore has been concentrated, that means once the gangue has been removed, now we will focus on extracting the metal from that particular concentrated ore.
Sir,
Yes,
sir, I don't understand, sir. Third point.
third point.
Yes,
Third
sir.
step. Don't say point, say third step.
Okay,
Okay.
sir.
Third step. So what is the third step telling us now? So the third step is extraction of metal. Now, what is the meaning of extraction of metal? The ore has been concentrated in the second step. What is the meaning of that? That means we have removed the impurities like sand, dust, clay particles, and whatever other types of impurities were present. Those impurities have been removed. But after removing the impurities, what I have right now with me is the ore, but the ore itself is present. I don't have only the metal, I have the ore. From the ore, I need
Sir,
the metal now. The ore may be what? Maybe the ore is magnesium carbonate like MgSO3, or the ore could be calcium carbonate like CaCO3. The ore could be something else like AgCl. I mean, anything. So from that, I need only the metal. How do I obtain the metal is called extraction of the metal. So only and only the metal will be obtained. I don't want any other thing which is present. I just want the metal out of the ore. That process of obtaining the metal out of the ore is called extraction of the metal. There are various techniques used. The first point is this, that is the concentrated ore is converted into the oxide of the metal. That means what? Once I have the concentrated ore, I will convert it to the oxide of the metal through some chemical reaction. Once I have the oxide of the metal, I will convert that oxide of the metal to the metal by carrying out reduction. Why reduction? Because if any metal oxide is reduced, I will get the metal. If any metal oxide is reduced, what will happen? I will get the corresponding metal. Because ultimately I'm interested in obtaining the metal only. So the concentrated ore is converted to the oxide of the metal first. Why so? Because remember one thing, it is easier to reduce an oxide of a metal than to carry out reduction directly. So it is ensured that the ore is first converted to the oxide of the metal. For the conversion of the ore to the oxide, there are two important methods. First is calcination. Calcination is the process of heating the ore in the absence of air. So one important part is absence of air. That means no oxygen is allowed to react with the ore. So why do we do calcination? Because we want to convert the particular ore to its oxide, that means to the metal oxide. If calcination is done, then what happens is the ore gets converted to its oxide. For example, if it is a carbonate ore, then the carbonate ore can be converted to the oxide with the help of this calcination method. Because ultimately I want the oxide. So if I have the carbonate of the metal, I will heat it, and if I heat the carbonate, I will get the oxide of the metal. That is one purpose of doing calcination. The other purpose is to remove water. If any water is present along with the ore, that will be evaporated out because I'm heating the ore. So the water will go out. And also I want to remove some other volatile impurities. The volatile impurities will get heated, and due to the heat supplied, they will move out as gases. Due to the heat supplied, all volatile impurities will move out as gases because I've heated them. So ultimately, I'll be left only and only with the oxide of the metal. Examples. If you look at the first example, you have a carbonate ore. CaCO3 is a carbonate ore. I'm heating it in the absence of air. And if I heat calcium carbonate in the absence of air, I get calcium oxide and carbon dioxide. So CaO plus CO2. CO2 will escape as a gas. So it was like a volatile impurity type. It will go out as gas. What I'll be left with is only calcium oxide, CaO. Similarly, in the second reaction, if I heat magnesium carbonate, I will get only magnesium oxide. Carbon dioxide will go out as a gas. Carbon dioxide will escape as a gas, and I'll be left with MgO, that is magnesium oxide. Look at the third example. Now here we don't have any carbonate, but still I have carried out calcination. Why? Because on heating that particular ore, I will remove moisture. That is, all water particles will be removed. So H2O will escape as a gas due to the heat supplied. So water will escape as a gas. Once water escapes as a gas, I'll be left with Al2O3. So only Al2O3 will be left behind. No water molecule will be present because water molecule has escaped as a gas. That means calcination is also helping us removing moisture and other volatile impurities which tend to escape as gases on heat supplied. Right. So due to the heat supplied, all volatile impurities and the water molecules escape as gases, and we are left only and only with oxide of the metal. Very, very important examples these are. You must know these examples of calcination. So CaCO3 has been heated to obtain calcium oxide. MgCO3 has been heated to obtain magnesium oxide. Al2O3.2H2O has been heated to obtain Al2O3, that is aluminum oxide. All these processes have been done in the absence of air. No oxygen has reacted with any of these. When I say that the process is taking place in the absence of air, that means I'm not allowing that component to react with oxygen. You don't see any oxygen reacting here in any of these reactions. It is just a heating process that happens. Temperature is increasing, and that is why we are calling it heating. Due to the high temperature, all kinds of volatile impurities go out as gases, and the carbonates get converted to the oxides, and the water molecules also move out. The moisture goes out as water, that is, gas, steam, you can say. Gaseous form of water is steam. So that goes out because we don't want any volatile impurity. We just want the oxide of the metal. That is why you see I wrote A, B, C, three purposes. These are the three intentions or the three purposes of carrying out calcination. Similarly, there is another process called roasting. So under this process, that is under the conversion of ore to its oxide. Conversion of ore to oxide. There are two processes under this. One is calcination and one is roasting. Both calcination and roasting ultimately give us the metal oxide. The metal oxide is obtained as a result of calcination or as a result of roasting. Calcination gives me metal oxide. It removes all the volatile impurities and water molecules. Similarly, roasting also removes all the volatile impurities and water or moisture. But now the difference between calcination and roasting is that roasting is the process of heating in the presence of oxygen. Calcination was done in the absence of oxygen. Roasting is done in the presence of oxygen. When I say the presence of oxygen, that means that reaction is taking place with oxygen. That means oxygen is acting as one reactant in that reaction. Oxygen will react with the particular ore to give me oxide of the metal. So the objectives of roasting are, first, to convert sulfide ores to oxides. Definitely, ultimately we want the oxide of the metal, so we are doing calcination and we are doing roasting. So it is used to convert the sulfide ores to oxides. Also, it is used to remove the volatile impurities and also to remove the moisture or water present in the ore. All those volatile impurities will go out as gases. Since they go out as gases, we will be left only and only with the metal oxides. Roasting happens in the presence of oxygen, and therefore oxygen is acting as a reactant. Examples of roasting. So if you look at the first reaction, ZnS, that is zinc sulfide, is reacting with oxygen. This process is called roasting. When zinc sulfide is reacting with oxygen, you get ZnO and SO2. So if you look at the products, ZnO is obtained as a product. ZnO is an oxide of zinc, it's zinc oxide. SO2 is a gas. SO2 is a gas. Similarly, if I look at the second reaction, in the second reaction I see that PbS, that is lead sulfide, has reacted with oxygen. Right. So this PbS will react with oxygen. If PbS reacts with oxygen, we get PbO plus SO2. Again, if I look at this, PbO is lead oxide. Lead oxide will be obtained as a product. So as a result of calcination and as a result of roasting, we have obtained oxides of metals. We have not yet obtained the metals. We have just obtained the oxides of the metals. So that is one part which is accomplished. That is, we have obtained the oxides of the metals. Now, the next task will be to convert the metal oxide to the metal, because ultimately we want the metal. So the next task will be to convert the metal oxide to the respective metal. If ZnO is obtained here, for example, then ZnO must be converted to Zn, because I need zinc ultimately. So zinc will be obtained if I reduce ZnO. Why am I calling it a reduction process? Because I am removing oxygen from ZnO. Removal of oxygen is also called reduction. So if ZnO is reduced, I will get Zn, and that is why I am calling it a reduction process. Similarly, if I want to obtain any other metal, then also I have to reduce that metal oxide. Reduction of metal oxide to get metal is called a reduction of oxide. That is, it is called final step of extraction. That means I have obtained the metal once I reduce it. When we obtain the metal after reduction, after that also there is another last fourth step which is pending. That fourth step will be refining or purification of the metal obtained. That means I want to purify the metal which is obtained. So that will be the last step of metallurgy. That is the fourth step. Because after obtaining the metal also there will be slight amounts of impurities present. Small amounts of impurities remain after obtaining the metal. So in order to remove all types of impurities, you do a purification process of the metal. And that is the final step. So before that, till now we have to do reduction of the metal oxide to obtain the metal. For reduction of a metal oxide, reducing agents are used. For reduction of a metal oxide, a suitable reducing agent has to be used. So if I want to reduce a metal oxide to the metal, I will react that metal oxide with a particular reducing agent. If I react with a particular reducing agent, then I will obtain the metal. So example, now if I want to show the reactions, let's do that. So reduction is carried out. Suitable reducing agents are used to carry out reduction of metal oxides suitable reducing agents are used to carry out reduction of metal oxides. Examples of some reactions. Examples. Examples of reduction of metal oxides. Examples of reduction of metal oxides. First, one very common reduction reaction is this one. So what have I done here? I have reacted ZnO, that is zinc oxide, with carbon. Carbon is acting as a reducing agent here, and I'm getting ultimately zinc metal as a product. So what is the process here? Carbon acts coke in the form of coke. Carbon is introduced in the form of coke. So coke, that is carbon, acts as the reducing agent. So here carbon acts as a reducing agent. Second one, Fe2O3, let's say we have Fe2O3 plus again carbon. Again here if you see carbon has acted as a reducing agent. Again I can write the same thing. Here coke or that is carbon acts as the reducing agent. For example, if I have Cr2O3, chromium oxide, Cr2O3 is chromium oxide. Chromium oxide is reduced with the help of aluminium. So I'll obtain Al2O3 and carbon and add chromium. I'll balance it. So again, if you see, I've obtained the metal, it is chromium. So here, who is acting as a reducing agent? So here I can say that here, aluminium acts as the reducing agent. So here, aluminium acts as the reducing agent. So you have to know these examples of reduction of oxides of lithium. Fourth one, electrolytic reduction is carried out for ores of highly reactive metals. You need not get into the details of this now, but just should know that for highly reactive metals like sodium, potassium, magnesium, calcium, sodium, potassium, magnesium, calcium, etc. So electrolytic reduction is carried out for ores of highly reactive metals. The process used here is electrolysis. The process used here is electrolysis. So these are the things that we should know for reduction of oxides of metals. 4 important examples. In the first one, we had carbon as a reducing agent. What was carbon doing? Carbon was reducing zinc oxide. What was the application for that? Ultimately, zinc was obtained as a metal. So zinc oxide was getting reduced to zinc by carbon. That is with the help of carbon. Second one, Fe2O3 is again ferric oxide, so it's an oxide of iron. Again, carbon is acting as a reducing agent in the second reaction. It is reducing Fe2O3 to Fe. That means Fe2O3 is getting converted to Fe with the help of carbon. So again, it is a reduction process. Third one, Cr2O3, chromium oxide is getting reduced to chromium. Chromium oxide is getting reduced to chromium. Who is doing the process of reduction? Aluminium. Hence, aluminium is acting as a reducing agent in this process. So, aluminium reduced Cr2O3 to obtains Cr. So, Cr2O3 has been reduced to Cr with the help of aluminium. And last type of reduction is electrolytic reduction. This is carried out for ores of highly reactive metals, like examples of highly reactive metals have been given in brackets. And the process used here is electrolysis. So the principle in the fourth point is for electrolysis. That is the principle. In electrolysis, you pass electric current and then finally you obtain the metal. But this method is carried out for ores of highly reactive metals. So they should sometimes ask you which are the metals for which electrolytic reduction is preferred. So then you will say that it is preferred for metals which are highly reactive, like sodium, potassium, magnesium, calcium, barium, and all these. That is why you must know the reactivity series which was taught to you in the previous lecture. If you don't know the reactivity series, it will be difficult for you. So you must learn the reactivity series and identify which metal is more reactive and which metal is less reactive than any other metal if you are asked to compare any two metals. So with this, we complete the reduction process. Extraction has been completed. That is the third step of metallurgy has been completed. Right? So what did we do under extraction? In extraction, first thing we did was calcination. The second thing we did was roasting. After calcination and roasting, we started the reduction of metal oxides. So reduction of metal oxide is carried out. After you have done calcination or roasting, you will do the reduction of the metal oxide. And these are the examples of reduction of metal oxide.